The last thing we're going to look at is understanding how real gases deviate from the ideal. Everything we've talked about so far, we're assuming that gases are behaving in an ideal fashion. But reality is oftentimes murkier than the ideal situation. So here are some ideal gases. Now we've said that molar volume, 1 mole of an ideal gas is going to give us a volume of 22.414 liters. But when I look at some of these real gases, chlorine, carbon dioxide, ammonia, nitrogen, helium, hydrogen, I'm starting to see some subtle deviations from that ideal. Okay. Well, what could be causing some of these deviations? Could be the molecular structure. Maybe gases do care a little bit what they're bouncing off of. We could also be looking at, situations where maybe we start to see more deviations if we change some factors. So we know the molar volume is at STP, standard temperature and pressure. But what if I change the pressure? Are we going to see more deviation from the ideal? Well, indeed we do. So if I take a situation where now I've increased the pressure, I've lowered the volume, I've squished everything closer together. And one of the characteristics of an ideal gas is the fact that everything is super far apart from each other. This is why we can compress down at a higher pressure. But once I do that, what starts happening? Well, the closer together things get, the more they start caring about what they're next to. If you think about it, let's say you go flying and you're in a row of 3 people and you're in standard seating. Well, there's not a lot of room, right? You're squished close together. And so every little jostle, you're interacting potentially with the person next to you. But now let's say you're in premium economy. So you've got a little bit more leg room, a little bit more distance between you and the seat in front of you, and the middle seat person doesn't show up. Well, now there's more space. And so now, when you move around, you're not necessarily going to be jostling every little thing. And so the person, sitting 1 seat away with that no middle seat taken, it doesn't matter as much. Okay. When I look at a real gas and I'm thinking about that diffusion, well, it's not necessarily just a straight line through, right? If this is my original gas particle here, well, as it's trying to effuse, it's bumping into a whole lot of other stuff on its path. So that can also affect, its ability to move through. Okay, when I look at real gases with increasing external pressure, again, that external pressure is going to squish down the volume. And so I've got the red line here for my ideal gas, but once I've deviated from ideal by changing that pressure there, now my molecular volume starts having an effect, because if I've squished everything closer together, what's happening? Oh, now there's not as much space between things, like that airplane. Hey, when I look at particle volume and intermolecular forces, my ideal gas doesn't matter what everything's next to it, but a real gas does. And so we get some of that deviation, especially at different types of pressure and temperature. Now this van der Waals equation, I am not going to make you solve anything for this, but you can see we get our normal PV equals nRT. Well, here I have pressure and volume, but my pressure has a correction for intermolecular forces and my volume has a correction for particle volume. And so this allows us to take into consideration that deviation from ideal behavior. And in fact, we can super deviate from ideal behavior. When I think about an inert gas like nitrogen, I can get liquid nitrogen. How do I get liquid nitrogen? Well, I have to cool it down quite a bit and I have to put it under extreme pressure. Okay. And so chlorine, under which conditions are we going to be least ideal? So take a look at that. Hopefully you said A. High pressure, low temperature. High pressure means I've squished everything closer together. Lower temperature means they're not moving around as fast, so they spend more time near each other. And so if they're all squished close together and they spend more time near each other, well, then those intermolecular forces do start becoming important, and they do matter. And so we end up with a situation where they condense down, and now my gas can go into a liquid phase. Okay. And then some important things with real gases, when I look at atmospheric gases and I'm looking at, the altitude and the temperature, we talked a little bit about that with, the situation of, at a higher altitude, the air is thinner because the force of gravity is weaker. And so we get, different pressures up there. Okay. And then when I look at, our ozone layer, this is really cool. So when I was a kid, so I was born in 81. When I was a kid, this was a really big deal, this hole in the ozone layer. And as we started understanding what was happening in the atmosphere and we banned things like CFCs or chlorofluorocarbons, and we started reducing down those reactions up in the atmosphere, we stopped thinning out that ozone layer as bad in certain spaces. So understanding gases is really important for understanding what happens up in our atmosphere and being able to continue to have a healthy planet.